In this video, we will begin looking at mathematical transformations of equations and graphs. A transformation is an operation that alters the form of a figure. Four standard types of transformations includes translations, the focus of this video, scale changes, which will include dilations and compressions, reflections, as well as rotations. To understand the effects of a translation, let's look at the graph translation theorem. It reads, in a relation described by a mathematical sense. Think of a mathematical sense as an equation in terms of x and y. The following two processes yield the same graph. First, we can apply a translation rule. Now, we're going to refer to a rule quite often as a mapping, as in, we're going to apply xy is mapped to x plus h, y plus k to the graph of the original relation. Let's go back to that rule or mapping. Both the x and y coordinates are being affected by h and k. Note that a translation is the shifting of a graph. So when h is negative, it shifts the graph to the left. When h is positive, it shifts the graph to the right. One way that I like to remember is h is the first letter of the word horizontally, as in horizontally shifted left or right. Now when k is negative, it shifts the graph down. When k is positive, it shifts the graph up. Now, unfortunately, k is not the first letter of the word vertically. However, I do also remember that h comes before k, just as x comes before y. So h affects the x coordinate, k affects the y coordinate, as if it was in alphabetical order. Another way to apply a translation is to replace the x by x minus h and y by y minus k in the mathematical sense, or your equation. Note the difference. When you apply a map, you add h and k. But when it comes to a mathematical sense, you will be replacing x by x minus h and y minus k. Let's look at various translation examples. And we'll begin by looking at the light blue graph, a graph that has not been affected by any form of transformation. That would be referred to as a preimage. Now that graph is of the square root parent function. And we're going to take points of that square root function, for instance, 0, 0, and map it to a new point, 4, 6. Just as we can take 4, 2 and map it to 8, 8. Now those are the only two that I'm going to show you with arrows, but we could have also mapped 1, 1 to 5, 7, 9, 3 to 13, 9, and 16, 4 to 20, 10. Those new points make up what we'll call an image. To identify our translation rule, let's go back to our original x and y coordinates and see how they were mathematically adjusted. The x coordinates were added by 4. The y coordinates were added by 6. Therefore, our mapping can be read as t of xy is mapped to x plus 4, y plus 6. The t in front is similar to function notation, where you identify it with an f, a g. In this case, t could mean translation. It could stand for transformation. Our original preimage graph was horizontally shifted right 4 units. It was also vertically shifted up 6 units. Thus the value of h is 4 and the value of k is 6. So how are we going to write the equation of our image? Well, we have to go back to the original parent function, and wherever we see y, we replace it with y minus k, or in this case, y minus 6. And wherever we see x, we'll have to replace that with x minus h. But please note, x is inside the radical. Therefore, x minus h, or in this case, x minus 4, must be inside the radical. Then we would simply want to solve for y, which means we'll add 6 to both sides, and our equation works out to be y equals the square root of the quantity x minus 4 plus 6. A translation also affects the domain and range. In this case, the original domain may have been all reals greater than or equal to 0. So is the range. But because x is the domain and x's are all being added by 4, our new domain has to be all the values of x greater than or equal to 4. And since our range is the y coordinates, and the y coordinates are all being added by 6, our range will now be y is greater than or equal to 6. Our second example will be of the quadratic parent function. We'll be able to take its vertex at 0, 0 and map it to negative 1, negative 5. We will also be able to take 2, 4 and map it to 1, negative 1. And if we had the points 1, 1, negative 1, 1, and negative 2, 4 on the original parent function, They would be mapped to the images 0, -4, -2, -4, and -3, -1, respectively. Note that all the x coordinates are being subtracted by 1, and all the y coordinates are being subtracted by 5. And you could say that when you write your rule or mapping. However, it would be preferred that you think of it as xy being mapped to x plus a -1 and y plus a -5, because that's the values of h and k. H is equal to -1 and k is equal to -5. Because h is -1, we can say it's being horizontally shifted left 1 unit. And because k is -5, we can say it's vertically shifted down 5 units. Again, if you want to write your mapping as xy goes to x minus 1, y minus 5, it's totally acceptable. You just have to remember that h and k were both negative. To find the equation of our image, we need to go back to our original pre-image equation, replace y with y minus k, or in this case, y minus -5, and replace our x with x minus h. But since x is being squared, we'll need to take x minus h and take that quantity and square it, or x minus -1 quantity squared. And then when we move the -5 over to the other side, we'll come up with the equation y equals the quantity of x minus -1, that quantity being squared, added by -5. Now that's probably not the way we would normally write the equation. I will accept it. But in the next slide, we'll see how it's most likely going to be written. Given the quadratic parent function's domain is all reals, and range is all y's greater than or equal to 0, the effect of the translation to this equation is going to be slightly unique. The domain is not going to change because all reals shifted left or right is still all reals. The range, on the other hand, being vertically shifted, will have y's now greater than or equal to -5. And before we leave, let's go back to the equation of our image. Notice that the equation x minus a -1 quantity squared can be rewritten as x plus 1 quantity squared. And then instead of saying plus -5, we can just simply say -5. Either form will be accepted. Our next example involves the hyperbola parent function, or y equals 1 over x. Now it's possible some individuals will recognize 1, 1 being mapped to -2, 3, and -1, -1 being mapped to -4, 1. But more often than not, it will be what's being mapped to things that are not found on the graph, but properties of the graph, that will make it easier to find our translation rule. In this case, let's look at the asymptotes. Specifically, we'll begin with the vertical asymptote x equals 0, or the y-axis. That's being shifted over 3 units to the left and coming up with an equation of x equals -3. Just as if we take the horizontal asymptote y equals 0, or the x-axis, and realize that's being shifted up 2 units and coming up with the equation y equals 2, we would then be able to recognize that our mapping is x plus -3, comma y plus 2. Again, the graphs were being horizontally shifted left 3 units and vertically shifted up 2 units. In order to find our new equation, take into account that h equals -3 and k equals 2. And when you replace y with y minus k, you'll go y minus 2. And when you replace x with x minus h, again, 1 over x needs to become 1 over x minus h, which in this case is 1 over x minus a -3. And when you add the 2 to the other side, you could write it as y equals 1 over x minus a -3 plus 2. And since the hyperbola parent function's domain and range is all reals not equal to 0, when you shift the graph to the left, the domain now becomes all reals not equal to 3, and the range, when shifted up, becomes all reals not equal to 2. Once again, look at the new way we can write our equation. Instead of writing 1 over x minus a -3, you can also write it as 1 over x plus 3, and then go plus 2. Our newest translation example only provides the following information. Our pre-image is the absolute value parent function, and the pre-image point of 1, 1 has the image of 8, 10. So if we're going to find a rule for this translation, we'll need to understand that 1 plus h and 1 plus k have to eventually equal 8 and 10 respectively. Therefore, h is equal to 7, k is equal to 9, and we can either write the rule t of xy equals x plus 7, y plus 9, or feel free to write as a mapping xy goes to x plus 7 and y plus 9. So now if we're going to find the image of negative 5, 5 under this same translation, we'll have to take negative 5 and add 7 to it, take positive 5 and add 9 to it, and we'll come up with the point 2, 14. And to find the equation of the image, remember that y needs to be replaced with y minus k, x needs to be replaced with x minus h. But again, x is inside the absolute value, therefore x minus h is inside the absolute value. And with h equaling 7 and k equaling 9, y will get replaced with y minus 9, x gets replaced with x minus 7 inside the absolute value, and when you move the 9 over by adding it to both sides, you get y equals the absolute value of x minus 7 plus 9. For this example, we're going to identify the translation rule that maps y equals the absolute value of x to y equals the absolute value quantity of x plus 3 plus 8 and describe its effects. The way I would approach this problem is to work from both ends, meaning I'll start with the preimage y equals absolute value of x. I will then use the graph translation theorem and replace y with y minus k and x with x minus h. Now let's go to the image of y equals the absolute value quantity of x plus 3 plus 8. That plus 8 is outside the quantity. Therefore, it came from the other side. And when I subtract 8 from both sides, I can rewrite it as y minus 8 equals the absolute value quantity of x plus 3. Now what I need to do is match my second line to my fourth line. Y minus k neatly matches up with y minus 8 as long as k is equal to 8. But what I really need to do is focus on x minus h matching up to x plus 3. And I can do that if I rewrite it as x minus a negative 3. Therefore, h equals negative 3 and k equals 8. With those values, we can apply that to our translation rule and say that t of xy goes to x minus 3, y plus 8, which means the graph has been horizontally shifted left 3 units and vertically shifted up 8 units. Let's do a similar example, this time identifying the translation rule that maps y equals x cubed to y equals x minus 7 quantity cubed minus 4 and describe its effect. We'll again begin with the preimage y equals x cubed and replace y with y minus k and x with x minus h. Remember, x was cubed, therefore x minus h quantity needs to be cubed as well. Let's go to the image, y equals x minus 7 quantity cubed minus 4. Recognize that the minus 4 is outside the quantity and therefore came from the other side. So let's add 4 to both sides and rewrite it as y plus 4 equals x minus 7 quantity cubed. This time I have a match for x minus h and x minus 7. H has to equal 7. On the other hand, y minus k needs to be rewritten so I can have y plus 4. I can do that by rewriting it as y minus a negative 4. With h being 7 and k being negative 4, my translation mapping is t of xy goes to x plus 7, y minus 4, which has the effect of shifting the graph horizontally 7 units to the right and vertically down 4 units. For our last example, I am told that the graph of y equals cube root of x is translated 1 unit down and 2 units to the left, and I'm being asked to find the image's equation and graph. To begin, I need to read my givens very carefully. 1 unit down is not my h. Up and down is actually the k value. It's left and right that tells me my value of h, and 2 units to the left means that h equals negative 2, and 1 unit down actually means k equals negative 1. Having the h and k values allows us to take y equals cube root of x, apply the graph translation theorem, and rewrite it as y minus a negative 1 equals the cube root of x minus a negative 2. Since y minus a negative 1 is y plus 1, we'll subtract 1 from both sides, and we can simply rewrite the equation as y equals cube root of the quantity x plus 2 minus 1. We'll use the values of h and k and apply its translation effects to known points on the cube root parent function's graph. So we'll take 1, 1 and shift it left 2, down 1 till we get to negative 1, 0. We'll apply the same translation to 0, 0 to come up with the point negative 2, negative 1, and negative 1, negative 1 so that we get the point negative 3, negative 2 on the image. When we plot those points, we produce the yellow graph, which is our translated image of our original parent function.